Next up, we have Nick Luther K9NL. The title of his talk is A Protocol for Multicast Weather Data Distribution over AX25. Nick?
Thank you, Steve. Good morning, everyone. I had a little bit of a late night last night, so if I fall asleep, one of you guys, maybe Larry up here in the front row, can come up and nudge me, and we should get through this. I brought my laptop up here. If I have time for a demonstration, we can do that. I don't think I will, so you guys can bug me later. I'm an electrical engineer from Oshkosh, Wisconsin. This is not too far away from me. I've been a ham for some time, and somewhere along there got interested in weather. The title of my talk is A Protocol for Weather Data Distribution over AX25. My paper in the proceedings goes into details on protocol issues, tables. I'm going to focus my talk somewhat on higher level system issues and more interesting aspects of the protocol. So I'm going to talk about the system for weather data distribution that this fits into. And then after that, we'll go into some protocol design issues and then future work and other things that I would need to talk about in a talk like this. So first of all, we need to start with the system requirements and the design challenge here. So amateur radio operators often get interested in weather data for one reason or another. A lot of them are weather hobbyists. We were talking about personal weather stations. A lot of them are interested in ARES or Skywarn or severe weather spotting. For one reason or another, they're interested in weather data. The reasons why I started this project are not necessarily relevant. For whatever reason, say you want weather data. My original purpose was providing it to spotters in the field. I grew into the project it is today for a more complete solution. And my goal is to handle any relevant weather data, to source it efficiently and rapidly, to move it over the internet, over radio, whatever. We're here to talk about radio, so I'll focus on that a little bit, and to present it to an end user in some usable form. So my next slide talks a little bit about sourcing actual data. When I began this project, say 2000, many years ago, we were using Perl scripts to pull data off FTP servers at the National Weather Service. That was a little inefficient. A couple years later, the National Weather Service opened up their NOAA port broadcast. That's the backbone to get data to all their weather forecast offices and centers. It used to be encrypted. You'd have to be a contracted concessioner to then obtain the data and sell it to someone else. And now it's open for all the taxpayers. A couple years after that, they changed the format to the DVBS standard. So now you just need a $30 or maybe $50, depending how much you'd like to spend, PCI receiver card off of eBay and the appropriate software, which I've written, and you're good to go. Voila, you have essentially all of the weather data used by the National Weather Service in the United States, less a couple products, and it's all free. And you're getting it at the same time those offices are, because this is the same network they're using. My next slide covers the architecture a little bit. Looks legible. So National Weather Service forecast offices with radar sites and centers. In this example, they have NESDIS, the satellite center. Send their data to a national control facility over wire, then it's uplinked, and then they all receive the data from other sites over the satellite broadcast with wire as a backup. So this is the main broadcast, and it's open for anyone who's interested. Also, this is officially an operational network. This is not like the National Weather Service website. It works if you can use it, and you're not to rely on that for protection of life or property. This is an operational network, though I certainly would not like you to use my tools in a mission-critical application. And we can discuss that and the reasons for that separately. But this is an operational network, unlike a National Weather Service website. So this broadcast can be used for operational purposes. It's the best source of data for what we're doing. It's easy to receive with a 10-foot C-band dish, and that's what we're currently using. We currently have 2 satellite receive sites in operation and 2 or 3 more planned. And if anyone would like to set one up, we can talk about that later. So the next system component is called RSTP, Radar Stream Transfer Protocol, or something like that. The initial group stuck. I can't remember what these acronyms actually stood for when I coined them. So this is another component I developed. It is kind of the sister protocol to what my paper is about and what I'll be talking about later in the presentation. I'm using it to connect all the pieces of this system. I have the satellite receive stations. I have packet gateways, you could call them, end user clients with internet connections, internet backbones, tools like I have a tool running to email my cell phone when certain statements are issued. We have archives, various tools. This is the component that connects them over TCP/IP, whether they're on the same computer or if they're an internet link, or they're on a LAN between a packet gateway and other infrastructure. This is a very reliable, mature protocol and has a mature implementation and has worked well. Supports authentication, compresses everything, it efficiently uses your bandwidth, has all the critical features for complex architectures, and this is GPL'd. This is a diagram of what the current network that I'm operating looks like. We have a couple satellite receive sites. We have a backbone node. We have relay nodes, so if you have a group of weather enthusiasts locally, you might run a relay node that taps the backbone and distributes the data to your local clients. RSTP and the RSTP implementation handle that on Windows or Linux, by the way. So it works pretty well. We can build some complex architectures. We can build redundant links where data will only flow one direction and then reverse if need be. To operate like a local satellite receive site, a local distribution node, other infrastructure. And of course, we can add packet gateways anywhere in this architecture. For the best reliability, you could add a packet gateway on that local site in the box over there as it's depicted. It has an internet connection to the backbone, and it has its own local satellite receive site, so if either one goes down, there's no single point failure. If you made 2 of those, you'd eliminate single point failures on the radio link. And that brings us to the real topic for DCC, moving weather data over radio. I know I've been pretty brief, but I've presented that we can obtain data for free, efficiently. We can process it with minimal effort. We can move it around the internet, build up networks. And now we've got it to our packet internet gateway site, what I will call an RDTP EX25 server. RDTP stood for Radar Datagram Transfer Protocol or something like that at some point in time. Another one of these initial groups that sounded really cool to me at one point, and the initials stuck. I don't remember what the name was. One of the goals of this project is to be efficient with low data rate radio links, so we have to prepare the data a bit. First of all, we're not going to send large weather data files over AX25 in most cases. So we have to filter the data stream and just the data we're interested. Usually that's radar and text for me. We'll compress it in the RDTP protocol. You can read my paper for a discussion of that. And we're going to do some extra preparation on radar data. That was the main purpose why I started this project. There was a 2004 QST article on that topic you could all reference, but I'll cover the highlights here. We need to take that radar data and do something with it to make a 30K, for example, NextRad file more appropriate. So here's what we're going to do. In my location, my nearest NextRad site is Green Bay, Wisconsin. I am in Oshkosh, Wisconsin, right about there. NextRad data is usually, most radial products are organized in radials, 367 of them out from the center, not 360, 367. And they have range bins, which are just slices of those radials. For most products, every 0.54 nautical miles, and you get 230 of them in a standard 124 nautical mile range product. Those numbers were all from my memory. I don't have them written down. One of them may be incorrect. You could reference an authoritative source if you needed to, but that should work well for the purpose of this talk. So if you want to not change the format, you can remove radials or you could remove range bins. In my case, if I remove 270 degrees worth of radials, I have a nice 90-degree slice, which is everything I care about. For some users, I understand that that would not be an appropriate processing technique, and it would be trivial to implement better processing schemes to maybe remove range bins. Maybe have all range bins on a couple radials, knock it down to half the range bins on some radials, skew which range bins you relay. It doesn't matter. That hasn't been implemented in software at this point, but could be done so trivially. This is what I do. This is a good start. I have tools that will perform this task on Windows or Linux. You give a simple script that's actually executed from the RSTP software, and this all happens on the fly quite efficiently. So let's go back to my last slide. This is for the file I showed on the next slide, which we were looking at previously. It started out at about 30 kilobytes. Once I stripped 3/4 of the radials, the size was down to about 7K. I can compress it a couple different ways. zlib is pretty popular these days. That gives you about 4.5K. I get slightly under 4.5K using bzip2. Though they're pretty close. They have similar licenses. Either one of them is open for commercial or non-commercial use as long as you credit them. So I chose to use bzip2. Takes more processing time, but the data is already so small, and we're using 1200 baud links. The trade-off is to process it more and make it smaller. Other systems have sent GIFs in the past. That's why I have these columns down here, or process data. If I process the original data into a ping image, it gets a little bigger, down to up to 40K. If I process it after I strip it, I still have, what does the slide say, 18K or so. So obviously, the thing to do here is send raw data, not send processed images, and process it at the end user's location. It also gives us advantages if we zoom in, we don't lose resolution. And that was an initial design decision. So we've configured a data stream. We've processed our NextRad data to make it appropriate for this purpose over a 1200 baud link. If we were doing a higher data rate, we probably wouldn't need to do this, or we would just send more data, more sites, or more products. The tool set exists to do all this. It's GPL'd. A lot of nice libraries. Everything is built on Windows and Linux. I'm not a big Mac user, so perhaps that could be done too. The only tool with a slightly different license is the no port receive software. I'm closely guarding that. If anyone uses it, I'd like them to connect to my network. That's my only license condition, so I have more redundant links. There is not really a comparable tool out there that's generally available for free. You'd have to be in the meteorological educational community to get the only tool I'm aware of. So that gives me a little bit of negotiating power to get people connected to my network. Otherwise, everything is GPL'd. So now we'll move on and start talking about the actual RDTP over AX25 protocol, which my paper was written about. I've mentioned a couple of these highlights already, introducing other system level issues and tools. The first requirement when I undertook this project back around 2000 or so was to make very efficient use of ubiquitous 1200 baud hardware. And that hardware still seems to be readily available, though it's not being used for much these days besides APRS. By doing radial stripping and other processing, I showed that we can make a very effective use of that hardware for moving weather data. We can move a a NextRad image, raw data, in a little over 30 seconds, give or take a little bit depending on what the weather is. That'll affect how big or small the file is. The last time I tested it a couple of years ago was faster than I could get it on the internet. When I obtained it from the NOAA link, I could send it over packet and still have the data at the other side of the packet link, this 1200 baud packet link, faster than you could get it on the internet from any source I was aware of at that time. That may not be true anymore today. I suspect if it isn't true, it's still a close race. So we have other hardware. People are interested in higher data rate experimentation, but when you've got those old 1200 baud modems in the old 1200 baud TNCs ready to go, and they're not doing anything, this is a reasonable use of them. So that's the main requirement. We have to use AX25. The modems that we have already available are built into TNCs, which only speak in AX25. So we're stuck with it. We don't necessarily need all the features of AX25. Some of them may in fact be undesirable for this project, but it lets us use this hardware. So that's why we're using AX25. And it also lets us use software AX25 stacks like AGWPE and then make sound card packet available. So other requirements, obviously we have to comply with Part 97 regulations, but at the same time, we'd like a multicast architecture. We would like multiple people to be able to receive this at the same time, and they don't all want to have their own connections back to a server. So we have to design multicast within Part 97 regulations and within the principles of the amateur service if we're using it over the amateur service. We have to handle NextRad Level 3 data. That's the raw data format for pretty much every radar product. Just about everyone in this room has probably seen since the NextRad system was designed in 1988 or so and deployed in the early 90s. If there are any meteorologists here, they are really active weather enthusiasts. You may have seen a radar product other than NextRad Level 3 from the National Weather Service, but those generally aren't that important for the purposes of this project and for most purposes most ham weather enthusiasts would have. So NextRad Level 3 radar data it is. That's the type of data that the numbers I had up before represented. So from that slide, we know that we're going to have to handle about 5 kilobytes. We'll get maybe a couple interesting products we'd like to send over any given link, whether they're from multiple sites or they're 2 different products from the same site. There are about 70 different NextRad Level 3 products. Most people in this room have probably spent most of their time looking at half-degree 124 nautical mile base reflectivity. That's only one of those 70 products, 70 or so products. And then we have to allow simple implementation. Other projects to do this sort of thing in the past kind of kludged together available tools, and you needed to be running then a certain version of Windows and have an appropriate tool to get to a BBS and then download a file and run some DOS program. And you've got a mess. This should be easy to deploy, and it should be designed to be that easy. And that involves designing for different operating systems to make every component operate on Windows and Linux, since most are fairly popular these days. I began this project before Mac was so popular. So we can't create any platform dependencies. That's a big requirement. Since we have the requirements, we need to get to the initial design decisions. I gave it a name, RDTP. We'll be using AX25 for the reasons I mentioned. Between the AX25 stacks that I used in my software development, I found that I was not always allowed to set whatever PID I wanted to use trivially. So I just used text, the hex F0 PID. I ran into some issues with source and destination call signs. Obviously, I want to have this multicast architecture. So source call signs weren't that big of a deal, but destination call signs, when I tried to listen promiscuously on Linux, it didn't work so well. It would have been non-trivial unless I made this design decision and used these AX25 destination call signs. So I defined RDTPC SSID 0 and RDTPS SSID 0 to be the two destination addresses used in this protocol. Messages to clients are sent to RDTPC, messages to servers are sent to RDTPS. I'll talk a little bit about that on the next slide. The clients and the servers too, likely. There's obviously this client-server architecture. A server has data and a client wants it. Neither should speak unless spoken to. They should both be polite band users. We need to obey the principles of the amateur radio service while we're multicasting. So we have to consider this politeness, and that resulted in a polling scheme, which I will discuss a little bit later. So let's talk a little bit about these RDTPC and S call signs. These are in the paper. There's probably a good reason documented in there, and I'll discuss them in this talk since they're a highlight. I said messages to clients go to RDTPC, messages to servers go to RDTPS. Then if you're working with the Linux AX25 stack and you're a server, you listen for your local address when you make your listen call is RDTPS via K9NL-15 or whatever the interface is. And then you get all messages intended for servers, and then you'll have to decide which of those are intended for you specifically. Clients do the parallel to that, vice versa. They listen for RDTPC via K9NL-whatever it might be. And in the AGW AX25 stack, that might not be an issue. I don't remember off the top of my head. Those are the only two AX25 stacks I used. And I would assume that this could be implemented without too much trouble in a different AX25 stack after I met all the constraints of these two. So these act kind of like multicast groups. They aren't really multicast groups per se, but they solve the promiscuous listening problem. And they allow us to use off-the-shelf AX25 stacks. That means current AX25 infrastructure, whether it be the AGW PE stack or the Linux kernel stack, connected to a TNC that the Linux kernel already supports, or the AGW already supports, or connected to a sound card that AGW supports. That using the existing stacks is important for supporting existing infrastructure. That's a main purpose, leveraging that, doing something useful with it, so it's not just sitting around transmitting your position. Sometimes you need to address a message to a specific station, though, and since we've just obliterated the AX25 destination call sign field, we need to re-implement that. That will be implemented in logical entity blocks, as I called them in my paper. I created that name as I was writing the paper. It wasn't in my spec. I just needed a name and an acronym, so we'll go with that. Also, there was an issue in the Linux kernel AX25 stack, so sometimes we need to identify ourselves, and I think I'll talk a little bit more about that later. We end up re-implementing a lot of AX25 to get around these things, and by the end, the only thing we're really using for functionally within AX25 is the source address for Part 97 identification requirements and the frame check sequence, the CRC at the end. So this is where we really start to understand the RDTP protocol. We've got a server. It's got data flowing in from somewhere, probably this network of no-port satellite receive sites and any other source, and it's probably running, there's probably an RSTP network providing that data to the server. So the RDTP, the packet gateway server, is probably itself an RSTP client. So it's got data flowing in. We have our DTP clients out there who want the data. And they're hopefully tuned to the same physical channel, the same frequency. And nothing's happening. So the server's idle, and the client has requests that the user entered. I want data stream name, whatever it may be, from such and such a server. And we'll reference that server by a call sign and SSID. So both are idling. Now, we don't want either side to make a lot of transmissions in its idle state. That would be bad. That would be irresponsible use of amateur service bandwidth. So we now have a chicken and egg problem. Who's going to talk first? And we're always going to have this in these sorts of protocols in this radio service. So the client has a rule, I don't speak unless spoken to. The server has a rule, I don't speak unless spoken to. The client realizes that the server should be sitting there and it's going to need to do something to start this. So what it will do in my current implementation is it will wait for a timeout period, say a minute or so. If it doesn't hear any RDTP protocol pulling, it will then speak up and say, hey, I have this data request. Assuming that the client actually has a request. So the user needs to enter data streams and servers it wants and into the client. And that's my second bullet here. Server's inactive, no polls are transmitted. The client waits for its timeout. The server validates that it has that data stream. It can acknowledge or reject. And it transmits that to everyone. All the clients should hear the multicast group, the RDTPC messages. So every client will hear that the initiating client's request has been acknowledged or denied. That's another opportunity for efficiency. So the client has this queue, call it a data structure, a container of data streams it wants to request. The server hopefully acknowledges its request after the timeout expires, sends an acknowledgement or rejection. That client then removes that request from its container of requests it has pending. All right. Any other client who might have wanted that data and might have had that request pending in its container for such pending requests also removes it because it's already been requested and acknowledged, so there's no reason to speak up and use any more airtime, any more bandwidth resources. So now the request is pending at the server. The server knows it has open requests for a certain data stream. It has data coming in that's organized into these logical data streams from upstream. So a data message comes in. The server says this message, whether it be a radar product, a text product, any weather data, I know this message comes from this data stream. Do I have requests? Yes, I do. I will transmit it. So the message is transmitted. It's compressed and everything. So it's pretty efficient, and hopefully it has already been processed upstream if it's radar data to make it much smaller, like the radial stripping we were talking about. And it gets sent out to all the clients. Clients receive it. Whether they wanted it or not, they parse the message and send it downstream. Now at this point, the server removes that data stream request from its pending request. It does this after a time delay because otherwise we'd have some timing issues. So the timing analysis works out nicely if we just wait a minute or two before actually removing it. But consider it removed at this point, or it's about to be removed. Clients know this. The client that has this request from its user knows that it just received data on this data stream. So its previously acknowledged request is now canceled, and it needs to log a new pending request. So it does that. It adds the data stream request to its pending request container. But now it can't speak unless spoken to. Everything is up and running. So the client will not speak unless spoken to, or unless a significant timeout elapses, another minute or two. And it will wait to be pulled by the server. So we'll talk about that in a minute here. It'll also call some hooks every time one of these events happens to it'll call hooks when data arrives to send it downstream. It'll call hooks when connections come up and down. The important thing is that we now have a new pending request. So at the server, one of two things could happen. The first thing is we're done. We've got nothing to do at this point. We've just transmitted data. No more data flowed in. So let's start a polling sequence. The other thing that could occur is that we might have more data that arrived while we were transmitting the last data product, or maybe it arrived simultaneously. If we still have a request, we don't want to go through a polling sequence. We just want to send that too. And that's why we have a timeout before we clear pending requests. It makes things more efficient and eliminates timing analysis concerns. So at the soonest opportunity, we'll start our poll. That means after we've flushed all the data we have to send to clients. We'll talk a little bit about polling a couple slides down the line. And for now, for the high-level semantics, we'll say that the server polls, does anyone have any requests? And the client responds, the initializing client, or any client who, from its user, has heard, I want this data, might respond and send its request. And we go through the same acknowledgement rejection process. It's acknowledged all the clients who have users who instructed them to ask this for this data now know that the request is queued at the server, it's acknowledged, and they take it off their lists. They don't need to transmit anymore. There might be two-way radio clients out there who never transmit because another client is always requesting their data before they need to. And they don't need to transmit. There's no reason they should, and this protocol will allow them to not ever transmit and make the most efficient use of the bandwidth and still get the data they're interested in. We'll go through a quick flow chart here and then talk a little bit more about this polling thing I talked about. This chart covers everything I just discussed. So this is from the client perspective. I could have made another one from the server perspective, but I had limited time resources, and I didn't want to bore you guys too much. So the client idles. If it has a request, I should have added trues and falses on here. Sorry about that. I think everything moving down the line is false, and everything moving to the right is true. I followed that convention, but forgot to add the trues and falses on decisions. So now that we have that out of the way, if the client doesn't have any data requests from its user, in that case there'd be no reason for it to be running. It can move down the line. This decision actually, I think, means does it have any pending requests in this pending request container that haven't been acknowledged by the server yet? If not, in this case, it would have already sent them. It moves down the line. Does it have received data packets to process? It'll process them. If it does have a pending request, there are the two cases we just discussed. Either we're just initializing, and we're going to have to wait for a time delay, make sure we're not pulled, and then transmit it. Or we're up and running, in which case we don't want to talk unless we've been spoken to, unless we've been pulled. So it'll wait for... this case, we handle polls separately, so in this case, it's just a matter of time or elapse. If the timer is elapsed, we'll send the request. Otherwise, we'll just leave it pending. Then we move down, do we have any received data packets? If we do, they could be polls. They could be acknowledgments, rejections of data stream requests. They could be weather data. If they're a poll and we have pending requests, then it's time to transmit those. If we don't have requests, well, we don't need to do anything in response to that packet. We won't speak it out. We'll just leave it go by. If we receive acknowledgement or rejection messages from a server, we need to remove that data stream from our pending request list. If it's rejected, it's going to be rejected again next time. There's no reason to ever ask for it again. If it's acknowledged, we just remove it from the list, and we realize the next time we receive data from that product, we'll be enqueuing it again. If we have weather data, we call our data hooks, and I have another block that we're going to need to enqueue that data stream request because it's going to be cleared on the server, and at the next poll, we do need to transmit that. So I've been talking about polls for 5 or 10 minutes now. How do these actually work? Well, this may or may not be the best way to do the polling in this protocol. It is the algorithm I decided on many years ago when I started developing, and I've used some subset of it, and it's worked. So I define 3 types of polls. Call sign specific polls first. If a server has actually talked to a specific client, and the client is making requests, we don't want to have a free-for-all at the next poll where everyone transmits and clobbers each other. So we can specifically pull one call sign in SSID and say, do you have anything for us? That client sends its requests, they get acknowledged, and we keep moving. All the other clients hear it, and they move it from their list, they never speak. And if we're actually transmitting data, we obviously have a request from someone. So there's always going to be a reason to send a call sign pull. It'll always make sense to do this, and it is probably always going to be the most efficient way to do things. In most configurations, there will probably only be one data stream with everything that the people using that server want. So that will mean there will only be one client operating at any given time, and that client can always be addressed specifically by call sign. And if everything else works out and all the stars align, no one should clobber that client and things should be efficient. Now, we still need to make an open poll to everyone. If anyone anywhere did have another request, there's a time for them to transmit. That's what an open poll is for. And then I also defined a concept of level polls. I haven't actually used those in practice, but they're a method for sorting out any open poll clobbering, we'll call it, that could occur. And in practice, that's probably not an issue. So the protocol doesn't specify what an implementation will actually use from these polls. A specific implementation could just implement open polls, and it would probably work fine. Call sign polls work nice too. If you want to use level polls, I put them in the protocol. I haven't really used them much. And it's up to the server to decide how it is going to poll. A client, of course, if it's going to be compatible with multiple servers, should support all of them. And my implementation that I've written does, in fact, support all of them from both sides. So let's talk a little bit about these level polls, though it's not terribly relevant because I doubt anyone would ever actually use them. I haven't found them to be necessary for efficient operation. So we're trying to resolve this problem. The network comes up, or we've got a server idling. We have two clients, and they both are started around the same time and send their requests. Or a better scenario would be we have the network operating, multiple data streams are offered by the server. One data stream is currently being transmitted and being requested by a client. Two more clients come online. They both want a second data stream. They're both going to respond to an open poll the server is going to give, and they might do so at the same time, and that would be inefficient. Well, if one of those stations is of a different type than the other station, those types could be represented by access levels, and that could be used to mitigate the problem. That the probability of that scenario occurring in practice is proven to be pretty low, so it's not that big of an issue. But the protocol, as I've documented it in my article, has 4 bits assigned for an access level. So we can give 16 access levels. That's more than we will ever need. You could use it to give priority to critical stations, or just randomly assign them to help mitigate any open poll issues. But in practice, it's not likely to be an issue. The paper defines whether 0 or 15 is the highest access level. If you ask me right now, I'd have to reference my paper. And it's configurable on the client. In the client configuration, what the access level is, that user can enter it. And if it's wrong, the server will correct the client with a message. I don't believe it's documented in the paper, but it is in my protocol spec. Special logical entity block, I called it LEB, saying K9NL-1, your access level is 1.3 or whatever it might be. And that is really the basic summary of the protocol. All the details on all the different packets that I've used, the packet types, well, they're not all in the paper, but the important ones are in the paper. The rationale for why it is that way is there. I've tried to focus on the highlights, how the semantics work, how the flow works as we go through a session. It's proven to be pretty effective, and I'll give some concluding comments on that. First of all, I'm going to talk about some future work. Right now, the protocol supports N+1 parity forward error correction. That was really easy to implement, to get one packet of forward error correction. Typical radar data transmission might be 20 packets or so off the top of my head. Someone with a calculator can probably correct me. And so that's something, and you're guaranteed in that many packets to miss one, so the n+1 parity just gets you a chance. A real forward error correction scheme, a block FEC scheme like Reed-Solomon would be most appropriate since this is a block-based protocol. That's probably a weekend project. If that ever hits the top of my priority list on a weekend, it'll be done. I have a specification document that needs to be cleaned up. I listed that on here. There's documentation work in general to be done on this project. And there's some call sign issues, some other bugs that I'm including my solutions to right now. If anyone's ever done any Linux AX25 programming, you know that the only way to really get all the headers correctly from AX25 packets is to actually get the raw data from the kernel and parse it yourself. And I'm not really into that. So I'm using a higher level interface, and I don't get correct source call signs. That means in each of my packets under AX25, I need to again include a source call sign because it just becomes relevant in many scenarios. That's inefficient. I could take the time in a weekend to get those raw packets and decode them and just set all my software to stop transmitting that. There's a bit flag for its presence in the headers. So it would be trivial to turn that off and gain the efficiency back. That's another project. Outside of RDTP on my higher level system of obtaining, sourcing weather data and sending it to clients by whatever means internet, radio might be available, there are a lot of things to do there too. One of them is processing more types of data. Right now, I am obtaining level 3 NextRad data, whether it be reflectivity, velocity, any other product, in all their different scan levels. I'm obtaining various text products, and I am obtaining Gini formatted satellite data in only Lambert conformal grids. I can process all that stuff, and it's cool, but there's a lot more available, and that might be applicable for the purposes of this project. That's an important task that could be done that would make all these tools more valuable. So handling more data, more types of data is definitely an open request, or an open future work area. Building network infrastructure is important. I only have 2 satellite received sites. If you have more redundancy. That would be nice to put some more up. And I've got a couple people interested, and I'd be thrilled to find more. Or even putting up AX25 gateways, these RDTP servers, as we call them. My station only operates part-time. I like to use it for development work. It would be nice if people, if they didn't want to put up satellite sites, if someone here wanted to put up a RDTP server and use this tool locally, it'd be great. It would get tested. Maybe it would spark development interest, and I would gladly supply the data stream over the internet. And then the end user GUI. I'm not going to have time to demonstrate that, but I will tell you right now that there is a nice end user GUI available that runs on Windows or Linux. It's based on WX widgets for the GUI library. It speaks to AGWPE on Windows over a TCP interface that's proven more reliable for me than the other IPC scheme. I forget what it's called off the top of my head that AGW uses. It also works with the Linux AX25 stack, Linux kernel AX25 stack. It displays data as it's received, provides a nice connection manager interface. It's simple but gets the job done, and it brings in all my graphics processing software. So you get menus that say, I've received KGRB, AWIPS PID, N0RGRB at a half-degree base reflectivity, and it gives you a history list of the last 10 that's configurable. And you just pick it off, it shows up on your screen. You can do the same for text products. It'll bring in data from multiple sources, could be internet and radio at the same time, or multiple radio and multiple internet sources. So I've got a GUI, but someone who's into GUI development could take it further. Most important thing is network infrastructure building at this point in the project to move forward. And I'm hoping that I might find some people here who are interested in that. And even if it's just deploying certain tools in this system. So that's going to be one of the first of my closing thoughts here. The system works well. I've been using it for years. Everything works. Everything could have more features or perhaps even work better, but it works quite well right now, actually, and you could use it right now. And I have been doing so, and I found it to be a lot nicer than other ways of obtaining weather data for my own personal use. I use it at work even. It's cheap to deploy. You might want to put up a packet gateway. You need your TNC and radio. And Windows or Linux, you can run free tools and free software for me, and you get a data stream from me for free. If you want to put up a satellite receive site, you need the dish. That's a problem for some people. It's got to be big, but the receiver card is only $30. And the tools you'll get from me for free as long as you provide me a data stream back. That's all I ask. And it should work quite well. The important thing, really, the first project goal is more infrastructure development, and I'd love to talk to anyone who is interested in implementing that type of infrastructure. A couple quick references. There's a QST article on stripping data for this purpose. This is before I developed the protocol. There's not much there that you didn't get from this presentation in the article and the proceedings. And I stole one graphic of NOAA architecture from the National Weather Service, borrowed it, so I cite them. That is the link for the NOAA users page. There's not much there otherwise than outdated documentation. I'd like to acknowledge contributions from these individuals, Aaron Heiss, Stephen Williams, and Jerry Parks. Whether testing our infrastructure deployment, they've helped me very much throughout the years, and even design discussions. And finally, if you're interested in deploying any infrastructure or being a part of this project, software development would be really cool too. I'd like to divide labor. Please contact me. I will be here today and tomorrow, or an email would do just fine. And one of those websites probably has all my GPL software on it too. So that's all I have for you today. Thank you for your attention. And I have my laptop here. I can run demonstrations. I have some data from Hurricane Ike. I can run through my GUI client, if you'd let my GUI program, if you'd like to see that, see how it works. And I hope to talk to some interesting people here, have some interesting discussions, and possibly deploy some infrastructure out of this conference here. So thank you much.